Let X and Y be topological spaces, Y Hausdorff, A a subset of X, and F from A to Y continuous. Show that if G from A closure to Y is a continuous extension of F, then G is unique. Soup. What we know. Y is Hausdorff. So for any two distinct points, y1 and y2, there are disjoint open sets u1 and u2, containing them respectively. G from A closure to Y is continuous, if and only if, for every W open in Y, the preimage of W by G is open in A closure. W is open in A closure if and only if there is an open set V in X, such that W equals V intersection A closure. X is in A closure if and only if for every open set U containing X, U intersection A is non-empty. What we want. If G1 and G2 from A closure to Y are continuous extensions of F, then G1 is equal to G2, proving that there is a unique continuous extension. Intuition. We want to show that G1 and G2 are equal. The proof works by contradiction. Assume there is an x0 in the closure of A, on which G1 and G2 differ. Since Y is Hausdorff, there are open sets U1 and U2 containing G1 of x0 and G2 of x0. Due to the continuity of G1, the preimage of U1 under G1 is an open set that contains x0. Similarly, the preimage of U2 under G2 is an open set that contains x0. The intersection of these two sets is open and contains x0, which is in the closure of A. So by definition of closure, there is an element in A, A0, that is mapped by G1 inside U1, and is mapped by G2 inside U2. But these two elements are the same and equal to f of A0, because G1 and G2 are extensions of F, so they match F on A. Therefore, there is an element, f of A0, that is both in U1 and U2. This contradicts the hypothesis that U1 and U2 are disjoint. So the existence of x0 in the closure of A, on which G1 and G2 differ, cannot be true, proving the uniqueness of the continuous extension of F. Now, let's write down the proof with all the details. Proof by contradiction. Assume there is X node in A closure, such that G1 and G2 differ at it and reach a contradiction. Note that G1 at X0 and G2 at X0, assumed to be different, are in Y, which fits the Hausdorff hypothesis. By 1, there are open sets U1, U2 of Y, such that their intersection is empty. G1 at X0 is in U1, and G2 at X0 is in U2. By 2, the preimage of U1 under G1 and the preimage of U2 under G2 are both open in A closure and both contain X noro. By 3, there are open sets V1, V2, and X, such that the preimage of U1 under G1 equals A closure intersection V1, and the preimage of U2 under G2 equals A closure intersection V2. Note, X0 is in V1, and similarly X0 is in V2. Thus, X noro is in the intersection of V1 and V2, which is open in X. Recall that X0 is in A closure. So by 4, the intersection of V1, V2, and A is non-empty. Therefore, there is an element A0 in A, such that A0 is in V1 intersection V2. Hence, A0 is in A intersection V1, which is in the preimage of U1 under G1. OF at A0 equals G1 at A0, which is in U1. Similarly, F at A0 equals G2 at A0, which is in U2. Then F at A nor is in the intersection of U1 and U2, contradicting the fact that U1 and U2 have empty intersection. This contradiction implies that G1 at X equals G2 at X for every X in A closure.